Hot diggity donut. We're on 6.5. 6.5. We're going to learn it. We're going to learn a couple of laws in the next two sections. And the first one here, we're going to call it the law of signs. The law of signs. Not the good idea of signs, not the recommendation of signs, but the law. Right. So you got to obey the law here. So most of the triangles that we've been dealing with up to now have been right triangles. And of course, what makes a right triangle a right triangle? What's 90 degrees? Yeah, it's got an angle that's 90 degrees. And that means the other two angles have to add up to what? If one of them's 90, the other two have to add up to what? 90. Very good, because the sum of all three angles is what? 180. Yeah, in coordinate plane. Two angles that add up to 90 are called what? Just to get that out there. Two angles that add up to each other to 90 degrees. It rhymes with complementary. 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 Okay, very good. But there's a lot of triangles out there that aren't right triangles, and we call them oblique triangles. Oblique means not right. It's a fancy name for saying not right. Now, you have other classifications of triangles too, like scalene triangles. You remember what a scalene triangle was?
Wasn't it all? No, I think it was like one angle.
What? There you go. All three sides are different lengths. That's a scalene triangle. Yeah. An isosceles triangle means two sides are the same. Yeah, isosceles triangle. But we're going to be dealing, those are both types of oblique triangles. Now, if you remember from geometry, you had some cases, three pieces of information given to you, and you're trying to figure out, does that even make a triangle? And if so, what kind of triangle? Right? So a triangle itself has 6 parts, right? 6 parts. Triangles have 6 parts. They have 3 sides and 3 angles. And what we're going to do in this section is we're going to figure out what all 6 of those pieces of information are, given 3 of them. Okay? So we're going to be given 3 pieces of information. And we have to determine what's going on. So what types of information could we be given? We could be given what we call angle, side angle. That's what the A is for, it's angle, and S is for side. Angle, side angle. This picture demonstrates angle, side angle. You have this angle, and then you have the included side, and then you have the other angle. It could be switched around. You could add side angle, angle. Side angle, angle would be like this side, and then this angle and this angle. Okay? So either one, you have 2 angles and 1 side. This is what we're going to focus on today, 2 angles and 1 side. You have this case right here, which is the side-side angle case, or as I like to call it, the angle side-side case. Okay? I'm brave enough to call it the angle side-side case. And I like to call it the angle side-side case because we call it the ambiguous case. You actually have the possibility of no triangle being formed, 1 triangle being formed, or 2 triangles being formed. So it's a pain in the butt to try to figure out which one it is, right? A pain in the butt. So if it's a pain in the butt case, it's going to be the angle side-side case, right? And that would be this angle, this side, and this side right here, angle side-side. All right, then you have the side angle side case, which we're going to learn in the next section. But this one's pretty cool. This one's pretty easy. You have a side, the included angle, and the side. And then you have side, 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 which is a snake case, right? All 3 sides. If you have all 3 sides, you can figure out what the 3 angles are. All right, we'll do that in the next section as well. So today we're going to be focusing on the first 2, really. All right, so let's try it out on example 1. We have a triangle here, and the instructions say to derive the law of sines. Oof, well, how do you derive something? If you derived a batch of biscuits, you'd have to make it yourself, right? Derived a batch, you'd have to like grind the flour yourself, and you'd have to make everything just appear out of nothing, right? If you wanted a batch of biscuits. We're trying to get a batch of the law of sines. So we have this triangle here, and we have it labeled, okay? Capital letter ABC, capital letters ABC. We're going to use capital letters to represent 2 things. The name of the angle, so we can refer to it by name, and the size of the angle. And in geometry, you made a separate distinction between the 2. Not anymore. Capital letters are angles, and they don't matter where they go. When you're labeling this, you could have had A, B, C, whatever. But once you have your angles labeled, now the side lengths, which are the lowercase accompaniments to the uppercase, they go opposite the angle. So opposite angle A is lowercase a, opposite angle B is lowercase b, and opposite C is C. Okay? So there you go, A, B's, and C's. And A, B, and C is just arbitrary. You could use L, M, and N, or whatever you want. It doesn't matter. It's just 3 letters. So here's what we're going to do. First thing is we're going to go up to point C, and we're going to drop a perp straight down, which makes a 90-degree angle. We call this the height, or that's the informal name. You know what the formal name is? When you drop a perp down to the other side to make a 90 degree, perp means perpendicular. It rhymes with paltitude. Altitude, yeah, altitude. Your attitude more than your aptitude determines your altitude. There you go. We call this the altitude. I'm going to call it H for height because A for altitude is already taken by lowercase a. Now what I'm going to do is I'm going to look at the 2 triangles that I created. The first triangle that I created is this one here that I'm going to look at. And I'm going to look at this base angle A. So I'm going to write it out here. Sine of A is equal to what? Well, let's come up here and remember, sine of theta, it was y over r, right? But we're not on the coordinate plane anymore. So if you're not on the coordinate plane, y over r may not be the best choice. So we go back to SOHCAHTOA, which means it's what? Opposite over hypotenuse, the SO for SOHCAHTOA. So the opposite of A is H, and the hypotenuse is B. Okay, so I have sine of A now is H over B. I want to solve this for H. I want to solve it for the altitude. So all I got to do is multiply both sides by B, and I get B sine of capital A. All right, now at this point, I'm kind of stuck with what I can do, but I do know the altitude. I know the length of the altitude. It's always going to be the adjacent side times sine of the adjacent angle. All right, let's do it again for this triangle. All right, so for this triangle, I'm going to use base B, so I get sine of B equals opposite H over hypotenuse A. And just like I did previously, I'm going to solve it for H. So I get H equals A sine of B. And now I have this one. Well, what next? What next? If I have something equal to H and I have something else equal to H, what can I say about the something and the something else? They're equal to each other. Absolutely, they're equal to each other, right? If 2 equals 3 and 3 equals 5, 2 must equal 5, right? Not really, unless you count those as variables. So consequently, we get B sine of A equals A sine of B. And now on my new column, I'm going to solve for the ratios of the similar letters on each side. So to do that, I'm going to first divide both sides by, I'll divide both sides by sine of A. I'll divide both sides by sine of A. And what happens here is that those divide out. So I'm left with B equals A sine of B over sine of A. Now if you notice, I got my A's together. That's what I'm trying to do. I'm trying to get my A letters together. I'm trying to get my B letters together. So to get rid of the sine of B on that side, all I got to do is multiply by 1 over sine of B on both sides. Or divide by sine of B. It's the same thing. And so I end up with A over sine of A equaling B over sine of B. And lo and behold, what do you see? I see nice little ratios. A over sine of A equals B over sine of B. This right here is the essence of what the law of sine is. The law of sine says that there's a magic ratio in every triangle, and it's found by taking the side length divided by the sine of the angle opposite that side. And you could do it for any side and any angle, and every time it's going to be the same. Now, I could derive it for the letter C if I wanted to, but it would just involve drawing an altitude like right here, and I don't want to do that. I don't want to bore you with those details. So let's just add it in there. It works the same way. This is equal to C over sine of angle C. And that's the law of sines. That is the law of sines. Now this one is useful for finding side lengths. For finding side lengths. Why is it useful for finding side lengths? Because I have the side lengths in the numerator. And it just makes the algebra a little bit easier. So there is another version. You know, with the ratio, you can flip both sides, right? As long as you have a proportion, you can flip both sides. So if I did flip both sides, I get this version right here, which is the law of sines. This is the one you'll see in textbooks. Sine of A over A, sine of B over B, sine of C over C, they all equal each other. They all equal that magic ratio for that triangle. And now this one is for finding angles very carefully, and we'll do that tomorrow. Finding angles very carefully. And why is it used for finding angles? Because it has the angles in the top. If you can put your unknown in the numerator, it makes the mathematics or the algebra a little bit easier. And then this one down here is just a flip version with the side lengths in the top, and it is good for finding side lengths. And I say with reckless abandon because you're always going to get the right answer. With angles, you have to sometimes find the complement of the angle that the calculator gives you. A little bit more to it than that. But today we're just going to be finding side lengths with the law of sines. Okay, so anytime we have these two cases, this is going to be law of sines. Law of sines. Anytime, law of sines. Angle, angle, side, or angle, side, angle. Okay, so when we find the remaining three pieces of a triangle from the three pieces given, we say we're solving the triangle. Whenever we find the remaining three pieces from the three pieces that are given, it's called solving the triangle. So let's try it out on example 2. Example 2, solve triangle ABC if A is 36 degrees, B is 49 degrees, and A is 8. Okay, first of all, we need to know what we're going to use, law of sines or the law of cosines that we haven't even learned yet. How do we know this is law of sines? Two angles and one side. If you have two angles, one side, it's law of sines. Now, let's draw a picture. Let's draw a picture. The picture that I usually draw just for solving triangles is this. Just kind of draw it like that every time. And then how do you want to label it? I usually label the angles first. So I usually start here, A, B, C. And it doesn't matter what goes down first, in what order, A, B, C. But once you have that, then opposite that is A, opposite this is B, and opposite this is C. And now what I do is I put my information that was given into the triangle. So A is 36 degrees, and that looks good. B is 49 degrees. That looks good. And I don't know what C is, but I do know A is 8. Now, of the three remaining pieces, the two sides and the one angle, which of those is easiest to find? Which one doesn't even require the law of sines? C? Yeah, finding C, the angle C. Because we know that the sum of all the angles has to be what? 180. So we could do this. We could say angle C plus 36 degrees plus 49 degrees. Make sure you're putting the degrubble on there. That equals 180 degrees. So this is just arithmetic, right? Which is my favorite subject. I'm horrible at it. 85 degrees. I always put an equal sign there. I don't know why. Plus 85 equals 180 degrees. If I subtract 85 with the calculator or without a calculator, I get 95 degrees. Which might be the high for today outside. Who knows? It's getting there. Summers are coming, right? 15 days left of school, but who's counting? Everybody. All right. 15 days. Wow. Right. That's wow. Or is it 18 days? 18?
Oh, it was 18 on Monday. It was 18.
16? 18?
Like a week yesterday.
Anyway, less than 20. Fewer than 20 days left. Fewer than 20 days left. It depends if you come to school. Like one day you can say, I'm skipping. That doesn't count, right? So that doesn't count for your days. Everyone has a different total. All right, 95 degrees. 95 degrees. So now I have all three angles, and I'm trying to find the two missing side lengths. This is where the law of sines comes in. Which side length would you like to find first?
C.
C. C, Senor. Let's do that. So the way we're going to do it is we're going to set it up like this. C, the unknown C, over the sine of the angle opposite it, which is 95 degrees. We just found that one. That's good. It's going to equal, now we got to get this guy involved. If you're given one side length, you got to find the angle opposite. This is what I'm going to call the pivot guy. We're going to use him both times. We're going to use them to find C, and we're going to use them again to find B. So that's going to be 8. Sorry, 8. Uh-oh. There we go. 8 over sine of 36. Now, the reason I say to put your unknown length in the numerator is to solve for C, all you got to do is multiply both sides by sine of 95. So we're going to end up with 8 times sine of 95 degrees all over sine of 36 degrees. And now that we solved for C on our paper, guess what time it is, everybody? Not unit circle time, but calculator time. Now, the first thing you need to do is go to your mode, because default mode is radian, and we're back in degrees. So go down to where the function is, mode, and switch it to degrees. You don't want to do this in radians, trust me. And now we just type it in, just like we see it. Alpha y equals 8 sine of 95 divided by sine of 36. Take a double check, look at it one more time. Make sure you typed it in correctly, hit enter. You get 13.558 or 559, either one. I'm a big truncator, big fan of truncating. And there are no units there, so that's just the answer. We found C. So if you want to add them to the diagram over here, 13.558, that's pretty cool. But realize that 13.558 is now a truncated or approximate answer. So I don't want to use him to find the other side. I want to use something that's more exact, which is 8 over sine of 36. So let's go ahead and find it. B over sine of its angle, which we know to be 49, is equal to, again, the same guy, 8 over sine of 36. He's pivoting from one value to the other. He's the pivot ratio. And then I solve for B, and we do show this on our paper, sine of 49 all over sine of 36. And now we just type that in. 8, alpha y equals 8 sine of 49 over sine of 36. And we get 10.271 or 272. I'll add that to my diagram. And now if you want, you can box all three, since we found all three. That just makes them easier to find. Do we have all 6 pieces of information? Yeah, if you look at your diagram, all 3 are labeled on the outside, all 3 are labeled on the inside. We did it. We did it. Lo hicimos. We did it, yeah. That wasn't too bad, was it? Law of sines? Not bad at all. Not bad at all. All right, let's look at an application of it, because you don't want to just be doing boring problems. You want to apply it somewhere in the real world. A satellite orbiting the Earth. Boy, there's tons of them up there, aren't there? Passes directly overhead at an observation station in New Braunfels, Texas. Hey, anyone ever been there? Yeah. Apparently there's an observation station here. This is not a fictional problem. And its stepsister city, Ardmore, Oklahoma. You probably didn't know that before coming in today. You probably knew our sister city, right? What's our sister city? Braunfels, Germany. Yeah. Well, what's our stepsister city? Ardmore, Oklahoma. Yeah, yeah. Now you know. Now you know. Now you know. How far apart are our stepsister cities? 340 miles apart. And we're going to call that a straight line distance. So here's the ground. We're going to say that this is New Braunfels, and this is Ardmore over here. And I know the Earth is curved, but for simplicity, we're going to say that it's a straight line distance, and it's 340 miles. At the instant when the satellite is between 2 stations, its angle of elevation is simultaneously observed, incidentally, by 2 stepsisters. 2 stepsisters and cities. That's pretty cool. To be 60 degrees in New Braunfels and 75 degrees at Ardmore. How far is the satellite at that moment from both of them? So let's put the satellite. We'll put the satellite right here. It looks like a bow tie. I'm going to draw a line from here to here, and I'm going to draw a line from here to here, and I'm going to label what was given in terms of the angles. This was 60 degrees, and this was 75 degrees. Based upon the angles, do you think it's closer to New Braunfels or to Ardmore? Probably Ardmore, right? The angle's steeper, that means it's closer to it. But we'll verify. So I'm going to go ahead and label these now. I'm going to call this B for Braunfels, New Braunfels. I'm going to call this A for Aardvark or Ardmore, I guess. And I'll call this C for satellite, right? Sattelite, satellite. And the opposite sides, so the distance between them are little c, and then little a is the distance from New Braunfels, and little b is the distance to Ardmore. Step one. No, the only thing that matters again is the lowercase letters have to be opposite the uppercase letters. You could label A, B, C in any order the first time, but then opposite the sides go the angles, and opposite the angles go the sides. That's the important part. All right, the easiest thing to find again is the angle, so let's go ahead and do that. We know that angle C plus 60 degrees plus 75 degrees has to equal 180 degrees. So that means, I don't know, I keep putting equal signs. 135, 180, so C is equal to 45 degrees. Is this a right triangle? No. It's a what? It's an acute triangle. That's another way to call it, yeah. It's probably a scalene triangle, right? And those all fall under the giant umbrella of something that's not a right triangle called an oblique. Very good. An oblique triangle. Yeah. Now, if this were a right triangle, the law of sines would actually work on it still, believe it or not. Law of sines works for right triangles and non-right triangles. It's pretty fantastic. All right, so now let's go ahead and set it up. I'll find, since New Braunfels is little a, we'll find a first. So I'm going to say a over sine of the angle opposite a, which is 75 degrees, equals the pivot. Who's the pivot guy? Well, we know it's C because we know the distance there. So the pivot guy is C. So we're going to have 340 all over sine of 45. And then we multiply both sides by sine of 75, and we get A equals 340 times sine of 75 all over sine of 45. And now we just type that in. So here we go. Alpha y equals 340 sine of 75 over sine of 45. 464.448. And because this is an application and this is our final answer, we need to add what to the end of it? The units, right? What are they? Miles, yeah. So add miles to the end. Wow, 464.448 miles. That's almost close enough to reach out and touch, right? Satellite, oh satellite. What are you doing tonight? Oh, I ran out of room. Let's come up here and find the other guy. We'll do this 464.448. And then the other guy here, we'll find him B over sine of the angle opposite B, which is 60 degrees, equals, again, the pivot guy would be 340 over sine of 45. And you just multiply both sides by sine of 60. And we get 340 sine of 60 all over sine of 45. Running out of room. So 340 sine of 60 over sine of 45. 416.413 MIL, miles. So yes, Ardmore was closer to the satellite, which meant they were getting better satellite reception on their satellite internet. Satellite internet is a big deal, right? It actually exists out there. That's what a lot of in Ukraine is using that to get access to the outside world via Elon Musk's product. No, not anymore. Did it blow up?
I don't know why I know this, but I think he like commercialized it, so they were using it for free, and that was like a big deal because there's different political sides with a private company that America owns a part in or something like that. So then you made it pay for it. It was like super expensive.
Like you have to pay now for the little verified blue flag?
I don't know that much.
Yeah, well, you know that at least. So I mean, that's good. Yeah, it gets politicized, and the bottom line is money. Yeah, unfortunately. But I imagine in the future we won't even have Wi-Fi like for our phones. We won't have cellular service. Everyone will have a satellite line, and everybody will be linked to on satellite. So you don't have to worry about getting service poorly anymore. You'll have it anywhere you go. That's in the future, I'm guessing. Only time will tell. The economics of it still have to be hammered out because everything's going to be expensive, expensive, expensive. All right, so there you go. Questions on that? Kind of fun? Not so bad? Okay, so that's when you have angle, angle, side, or angle, side, angle. But what if you're given the pain in the butt case, which remember is the angle, side, side? Yeah, I'm not afraid to say that, angle, side, side. We call that the ambiguous case. So what does the word ambiguous mean by itself? Unknown? Yeah, possibly unknown. That's a good one. Vague, right? Vague, unclear, iffy. Yeah, all of those could work. Yeah, and those all ring true to what we're doing. So whenever you have the pain in the butt case, you're going to have the possibility of, for the acute case, you're going to have three possibilities. All right, so let's say we're given angle A, the adjacent side B, and the side opposite A. So this is angle, side, side. See that? Angle, side, side. Angle, side, side. It could be if the side opposite the given angle, which is in this case A, if it's too short to even reach the other side. How many solutions will you have? Well, you could play with it like this. Think of C as being a hinge, and this arm that dangles down is the pivot length, the pivot arm, and then this side right here, side B, is fixed. We call it the boom side, B-O-O-M. It's the boom. It's fixed. It can't move because of the angle. But C can. We don't know what this angle up here. So if you swing this back and forth trying to reach the other side to make a closed triangle, it could be that it's too short. And then it could be that there's zero solutions, right? Zero solutions. It could be this. It could be that the side opposite the given angle is just long enough to come down here and kiss the bottom when it's hanging straight down vertically, which would be a right angle. So this case would be one solution, and it would be the right triangle case. It's just long enough to reach the other side. But it could be this one. This one's the cool case. It could be that A is a little bit bigger than B. So it can't go straight down. You have to kick it out a little bit. So you get this one triangle that's right here. Excuse me. But if you swing it through, it intercepts the base still on the interior of the original angle. And then you would get this obtuse triangle right here as well. This obtuse triangle right here. And that would give you two distinct triangles. So why is it ambiguous? How many triangles can you get when it's the pain in the butt case? Two or one or none or zero. Yeah, 2, 1, or none. I like that. None, 1, or 2. You can't get 3, can you? I don't think you can get 3. Yeah. I mean, the swing and arm kind of thing is a good way to visualize what's going on here. Now, what if A is bigger than B? If A is bigger than B, then as you swing it around, when it lays on top of B on its way to swing, it's going to be a little bit longer. So as it continues swinging, it intercepts the base outside the angle. And we call that a reflex angle when it's outside like that. That doesn't make the triangle. If it swings outside the triangle, it's no good. So that's another case where you have zero solutions. It's either too short or it's way too, well, that would be one solution, sorry. You would still get the one solution, but you wouldn't get the second solution. Okay, let's look at it a little bit more acutely, a little more acutely. When we have the acute case, we have these cases again. How are you going to know if the side opposite the given angle, which is now B, is too short? Well, you compare it to the altitude. And as we found up above, the altitude is a sine of b. It's the adjacent side times sine of the adjacent angle, right? That's the altitude, the height. So if that base is smaller than the altitude, it's not going to reach. There's no solution. In this case, if the base is exactly the same as the altitude, which again is a sine of b, then you're going to have the one solution, the right triangle solution. So that's going to be how we're going to analyze it. How do you know if there's two solutions? Well, the base is bigger than the altitude, but it's still smaller than A. It's still smaller than this adjacent side. That means that when you rotate it around, it fits back inside. So most of the time we're going to be having to compute the altitude and comparing it to that opposite side, the swing side. Now here are some other cases. Case 4. What if the side opposite the given angle is exactly the same length as A? You know you're going to have one solution here, but as you swing it around, it comes back up and it lays perfectly on top, right? Which is no solution there. So if A and B are equal, we have one solution, and it's the special what type? Isosceles. We get the isosceles triangle, okay? We already talked about this. If B is bigger than A, flat out B is bigger than A, there's one solution. One solution. And this angle down here is going to be pretty acute. Now that takes care of the acute cases. We might have obtuse cases. When the base angle is bigger than 90 degrees, we can have an obtuse angle. These are a little bit different, but you could probably visualize these when you draw them. If the side opposite the given angle is less than A, what's going to happen as we try and reach the other side if it's smaller than A? Are we going to reach this base? Not at all. So there's going to be zero solutions, no solutions. We're on case 7 already. What if they equal each other? Well, in the acute case, there was one isosceles triangle. But if they equal each other now, there's no solution because it has to be longer than A in order to reach the other side. So no solution. You can visualize that. And of course, if B is bigger than A, it's going to kick out here and you're going to have one solution. And of course, when you swing that long arm across, it's going to intersect way out here outside the angle. So that'd be no solution. So if B is bigger than A, you get the one solution. All right, if you understand what I just did, then maybe you don't even need this chart. I don't really like the chart. It summarizes everything, but it's not visual, okay? And I think visually it's a little bit easier to assess what's going on. And that's what we're going to do right now. Example 4. Example 4. All right. It says on example 4 only to determine the number of triangles formed by the given information. So we're not solving the triangles. We just want to figure out at this point how many there are. Once we figure out how many there are, and then a little while later, we'll go ahead and solve them. All right, so we have A, B, and B. So how would you recognize this, first of all, as being the ambiguous case? Later on, we have all these cases thrown in. You have two sides, and you have an angle. Now, it could be side, angle, side, or it could be angle, side, side. How do you know which one? Two ways, right? You either draw it, and then you could tell, or here's an easy giveaway. You have a repeated number, or a repeated letter, sorry. If you have a repeated letter, and you still have two sides and one angle, that's going to be the angle, side, side case. That's the pain in the butt case, all right? So I know that this is not side, angle, side. All right, now let's draw it. Draw your base of your triangle out here as far as you want. And then try to make your angle a little bit accurate. Our base angle is 122. So that's going to be obtuse. You want to make sure you're drawing it obtuse if it's obtuse and acute if it's acute. That's really kind of all that matters. All right, now let's label that as B, which means the side opposite, which I'll put right here. That's going to be side B. And then the other side that's given, that has to be A. So that's 4, and this is 3, and this is 122. Now, a lot of the times in these cases, you could draw it and figure it out without doing any calculations. What would you say? How many solutions here? I would say 0, 2. This is 3 and this is 4. So if I pivot this around like this, is it ever going to reach the opposite side? No. So now you just say no solution. Or no triangle. Either way. Pivot it around, it doesn't reach. It's a little bit short right there, a little bit short. It's 1 unit short. It would have to be bigger than 4 to make a triangle. So there you go. The obtuse case is pretty easy. Let's look at part B. You've got 2 sides and 1 angle. 2 sides and 1 angle. Is it side angle side or angle side side? Angle side side. Good. Why? Not because it's in this section, but because we have repeated letter. Yeah, yeah. So whenever you're drawing the angle side side, it's a good idea to draw it every time the same way. Give yourself that base, and then this is an acute given angle, so 56 is going to be right here, and that's going to be what we call C. And then the other side, I don't ever draw it all the way down. I just draw it a little bit ways down, and this is going to be C equals 11.5. And then the other side that you're given, that's just the adjacent side. So our pivot guy is up here. There's the pivot point. What would you say? How many solutions? 2? Well, I know there's going to be at least 1, right? Because when this thing comes down, it hits the ground right there. So there's at least 1 solution. But now the question is, when I swing that thing around, does it intersect on the inside of the triangle or on the outside? 11.5 is bigger than 11, isn't it? So when I swing it around, it's going to go outside, which is not a triangle. So how many solutions? Just 1. Just 1 solution. Letter C. 2 sides, 1 angle, repeated letter. Repeated letter. A and A. So again, it's going to be the ambiguous case. Draw your base all the way out. The angle is 36, so it's even shallower than before. And then that's going to be angle A. We call it angle A. And then the side opposite is side A. And then the other side that's given, you just call 12, or B. So here's your pivot right up here. Now what? Now what? 7 is less than 12. So now the question is 7 even long enough to reach the other side? And if it is it long enough to be kicked out to the side and generate 2 solutions? Or I don't think it's going to be swinging around and get on the inside. So, golly, it would be helpful to know this quantity right here, wouldn't it? It'd be good to know the height. If I could figure out the altitude, I compare it to 7 and get my answer. So if you want to just reinvent the wheel here, you could say sine of 36 degrees equals the opposite, h, over the hypotenuse, 12. So h is equal to 12 sine of 36. You're going to be doing enough of these problems if you're doing your worksheet to know that you could just find the altitude that way. So it's going to be 12 sine of 36, 12 sine of 36. But if not, just do the SOHCAHTOA. All right, I got to figure out what that number is. So I'm still in degree mode, so 12 sine of 36, that's going to be 7.053. 7.053. Now, what the heck does that mean? That means in order to reach the other side, you need to be at least 7.053 units. What is our swing arm's length? It's only 7. Does it reach the bottom? No. It almost does, right? If it sticks its tongue out or something, it might reach it. Or it stretches its nose. I don't know if you can stretch your nose, but maybe. So this is no solution. I'm sorry, it's no solution. But had that number been like 7.5, I'm sorry, had our side been 7.5, there would have been 2 solutions because 7.5 is less than 12. You would have had 1 over here and 1 over here. But the side length was 7. So anyway, I think that's enough for today. We'll pick up with these, and we should be able to finish. Tomorrow is the EOC test. So if you're in my class, you need to go to the auditorium if you're not testing. I'll be administering the test in the large gymnasium. Yeah. So we'll pick up with this on Friday. We'll finish on Friday. And then that means the worksheet will be due on Monday. I'm guessing that's what it's looking like. So anyway, any questions? Thank you. All right.